Before the authentication server went down in today's class, you were asked to project this vector onto this one and estimate the magnitude of the projection. Now, to project, we sketch a line from this vector perpendicular to this vector. Okay, because we're projecting the force vector, and obviously the force vector is the one that has units of force, or the displacement vector, which has units of displacement, so they're easy to identify. The projection, therefore, would be this vector here. Again, assuming that I have a good perpendicular. Now, if this is 20 newtons, that means the length of this vector represents the 20 newton force. What's this one? You should pause and think about that, but I'm going to say pretty quickly. So yeah, we could eyeball it. You know, this is about this long, and that's a little less than halfway, somewhat less than halfway. If we do 1, 2, 3, I'd say it's about 0.3 times this, about 30% of this. So if this is 20 newtons, this is probably around 6 newtons. So the magnitude, 6 newtons. A little question mark around that, but that would be a reasonable estimate of magnitude. Anything from 4 to 8 newtons would probably be a half decent estimate. It's clearly not 10 newtons. There's no way this projection is half the length of this vector. Okay, significantly less than half, and probably somewhat more than a quarter. So we have this estimate. Now, my next question is going to be, what's the product of this? Now, okay, first of all, this projection vector the projection of your force vector on your delta S vector, where the delta S represents a displacement of 50 meters, in this case, in this direction. That's your vector F parallel. Okay, so now how much work is done? Is done by the force. Acting through the displacement. And the answer to that is two answers, but the work, and I'll use a delta capital W for work because it's the work done on an interval of displacement. Your text would probably use just plain old W for that. I prefer the delta because, again, it's reference to what occurs on an interval. Now, if delta W, well, delta W is going to be F parallel times delta S. Now, there's no vector sign over these. These refer to magnitudes, except, as I've indicated before, the F parallel might actually be negative, so we're kind of treating this as a semi-vector. That's a little bit non-rigorous, but we can live with it because I'm going to do the dot product in a minute anyway. So delta W is F parallel, delta S, and F parallel is in the same direction as delta S. The F parallel vector is the same direction as the delta S vector, so that this is going to just be 6 newtons, and this is approximately equal to, okay, that's going to be 6 newtons times 50 meters, which is 300 joules. And of course that's newtons times meters, and a newton times a meter is a joule. Okay. Another way to have calculated this is F dot delta S equals, and I'm going to just assert that that's equal to the F parallel vector dot delta S which is equal to, see if I can get out of the way here, F parallel delta S cosine theta, where theta is the angle between F parallel and delta S. And that's just going to be the magnitude of F parallel times the magnitude of delta S times the cosine of theta, which is the cosine of 0 degrees. So that's 1, so this is 6 newtons multiplied by 50 meters times 1, which is 300 joules. Okay, so we can do F dot delta S in a variety of different ways, but one way is to simply estimate, or one way or another you can calculate. But from a picture like this, where we don't have any specific angle and so forth, your best estimate would be to estimate the parallel component of the force vector and multiply that by the magnitude of the displacement vector. Now, there are two possibilities. If the 20 Newton force had been back this way, then it would have had a negative projection on delta S, and the angle would not have been 0 degrees. It would have been delta S in this direction, F parallel in this direction. So the angle would be 180 degrees. The cosine of 180 degrees being negative 1, we'd have a negative 1 here, so we'd have negative work done by this force acting through this displacement. The final connection, and you wouldn't want to do an estimate by estimating this angle and calculating the cosine. You can estimate the projection much more accurately than you can estimate the angle. But if we knew the angle, let's call this angle phi for the moment, because I use theta over here for the angle between F parallel and delta S. Okay? F dot delta S is 20 newtons times 50 meters times the cosine of phi. And so if you did have a good estimate of the angle, you could use this to calculate your dot product. Or if you have this vector, if you have I and j components of this vector and I and j components of this vector, and you could estimate those, you could use the calculation of the dot product using the components, I component times I component plus j component times j component. I'm not going to write that down. Just there's your picture of the dot product of a force vector with a displacement vector. It's always the same. If you're estimating it, then you're just going to estimate the projection. And you know, we had a previous video where we did the projection. So you got to know how to do projection. You got to know how to do a dot product, but it's really not all that challenging.